again, so welcome back. So we have been discussing kinetics in our last class, right? So we'll take you through from there. So we have been discussing kinetics, or how fast is the reaction, right? And we talked about terminology. In general, we said we are going to talk about volumetric rate, and then we started discussing about sequential reactions, either parallel or series. Parallel, A goes to B or A goes to C simultaneously, and in here we are concerned about the branching ratio, right, or selectivity here, I guess. Branching ratio or selectivity here with respect to A goes to B and A goes to C. And in the same case, we said we are going to look at A goes to B goes to C, and in series we are concerned with what is the rate limiting step that controls the overall what do we say, chemical process here, right? In this case, we are now going to look at a few graphs, I believe. So here we have a particular graph here, and so the background information is, I guess this is for A goes to B goes to C, rate constants K1, rate constant K2 for the second reaction B going to C, right? And here on the x axis we have a dimensionless time here, that's normalized, I guess, right? Not normalized, pardon me. And here we have on the y axis a dimensionless concentration C by C naught, right? So it gives an idea about how it changes. So concentration of particular what do we say, component. So here we have A, B and C, right? And here we have rate constant. So for example, not for example, for now, think of rate constant as a metric that gives you an idea about how fast or slow the reaction is. We will talk about it in greater detail later on, right? So this is a small k, and we see that in this particular example K1 is equal to K2, right? And obviously what do you expect, I guess, A is decreasing with time, right? First order reaction, again we will discuss what they are. So A is decreasing with time, or this dimensionless time here, that is what you see. So as A is decreasing, as A keeps decreasing, you will have B increasing, and that is what you see in this particular phase here, right? So B is increasing. At the same time C will also increase whenever B is formed, right? So that is what you see here, and at a critical point in time you are then going to notice that B is going to start decreasing, and while C is going to keep increasing. So that is what you see here, right? So let us erase this and start afresh. So A keeps decreasing, B initially increases to a certain point, and when it reaches a certain concentration the rate changes again, right? And that is why you see that there is a net decrease. So initially there is a net increase and then there is a net decrease. With respect to C, you only see what we say formation here, right? So that is what you are noticing here. And at this point can we try to highlight which is the rate limiting step here? Difficult to, right? But in general, how do we identify that rate limiting step? Whenever there is an accumulation of your particular reactant, let us say accumulation of your reactant. So anyway, because you know the kinetics of both the reactions are relatively similar, or the rate constants are same, so that is why I guess it is difficult to identify what we say rate limiting step. But if you want to, I guess, just for sake of theoretical purposes, you can say it is accumulating here, or B is accumulating. So you can call B to C as the rate limiting step, but I won't go go ahead and call that, right? So let us look at another example where we will see a better what do we say, representation of the rate limiting step. So here again we have a second example here, A goes to B goes to C, again rate constants 1 and 2, I mean K1 and K2, but here the issue is that K1 is far greater than or greater than K2, right? And that is what we see here, K1 is 10 times K2. So what do you see here, I guess, right? A, what is happening to A? It is degrading to B, and because A going to B is very fast, right? That is what you see here, K1 is high, right? So what does that mean? A going to B is pretty fast, and that is what you observe in your particular what do we say, graph here. So A rapidly degrades to B, and it is already at equilibrium here, I guess, at least A, not the whole system though. So and then, but what happens to B though? So as A is degrading to B, so B is rapidly formed, right, but unlike in the previous case, the B to C reaction is slow here, that is why you see K1 is greater than K2. So the R net, you know, when we look at that, it's remarkably high, right, and so the formation reaction outweighs the loss reaction here, or rate of loss, pardon me, not the reaction here, and you see the loss is relatively slow. Why is that? B to C or K2 is slow. So what do you see here? You see accumulation of your particular reactant or accumulation of B. So here we can clearly identify that B to C is your rate limiting step, right, and for example think of this, I am able to go from Roorkee, Roorkee I guess, very fast to Ghaziabad, but at Ghaziabad I have a huge traffic jam, or I am hitting traffic and I have accumulation of traffic and I spend a lot of time there before I can get back to my preferred destination, which is C I guess, right. So that is what you see here. So let us look at that once again please. So here we have A going to B going to C, and A goes to B is much faster than B goes to C. So what is that happening I guess, right. So you see accumulation of B, right. So that is what you are seeing here in this particular case, A goes to B is relatively fast, but B going to C is relatively slow. So you have the rate limiting step which is B going to C, right. So let us move on to another example here. So here we have a same case, A goes to B goes to C, but here you see that K1 is far greater than K2, right, almost 100 times I guess, right, 2 orders of magnitude higher now, right. So what do you see here? So I guess the graph by itself might be relatively unclear, so we are going to look at a second graph that what we say looks at this particular region later on, but try to understand what is happening here. So in effect A goes to B goes to C, if you look at this particular time scale more or less looks like it is similar to just B goes to C, right. Why is that? You see that instantaneously I guess, at least for this time scale, all the A is immediately converted to B, right, and then you have a slow degradation of B to C. So that is why B slowly decreases while the concentration of C slowly increases, right. So in effect A goes to B goes to C transforms into just B goes to C, and why is the reason, what is the reason I guess? B to C is the rate limiting step, and also K1 is remarkably higher than K2. So to understand the system better, let us zoom in I guess. So here the scale is 0 to 500, and now we are going to look at the scale from 0 to 5 for the same example as we looked at earlier. A goes to B goes to C, K1 is far greater than K2, right, that is what we have here. K is the rate constant, right, and what do we see here now I guess? So we see that with this particular truncated time scale, we see how A is being remarkably degraded very fast, right, the kinetics of degradation of A are remarkably fast, yes, and at the same time B is formed remarkably fast, or the kinetics of formation of B are fast, we are just describing this process, right, but B going to C is very slow, and that is why you see it is very negligible here, right. So that is why what happens, B ends up accumulating, and so thus B going to C is your rate limiting step, right. So hopefully that is clear. So we will move on to the next set of examples I have. So a usual case that people come across is reversible and irreversible reaction, but keep in mind that these are only practical definitions, they are only practical definitions. So let us try to understand what they are, let us say. So for example let us say A plus B can go to C plus D. So in general theoretically you will always have a forward and a backward reaction, right. So when somebody says a particular reaction is irreversible, what does that mean? It is a practical definition again, because theoretically all the backward reactions are feasible, but when somebody says it is irreversible, what does it mean? That the kinetics of the forward reaction is much higher or faster, pardon me, than the kinetics of the backward reaction, right. So the kinetics of the forward reaction is much higher than the kinetics of the backward reaction, right. So in effect you see that people think that it is an irreversible reaction, but again keep in mind that is a practical definition only. So it is I guess no issue of equilibrium here, it is mostly kinetic controlled, not mostly, it is always kinetic controlled, it is kinetically controlled, right. Yes, so let us look at this example of here. What is this? A plus B going to C plus D, I guess. What is the equilibrium constant? This is the capital K here, equilibrium constant. We talked about that in the previous classes, capital K. And what is that equal to, I guess? Activity of C. Stoichiometric coefficients are all 1, so we are going to not look at that, act into activity of D divided by activity of A into activity of B. So more or less activity of the products in the numerator and activity of the reactants in the denominator, right. So this is what we have. So when let us say the rate of the forward reaction is far greater than rate of the backward reaction, what does that mean? So it means that C and D are going to be at remarkably higher what do we say concentrations. So again these are parallel reactions, right. So we look at branching and selectivity here more or less, we do not need to go into that in greater detail. So again here when somebody says that this particular system is irreversible, what does that mean now? It means that the numerator is remarkably high. Why is that? Because rate of forward reaction is far greater than the rate of the backward reaction. So everything as A and B react to go to C and D accumulate, but simultaneously C and D going back to or reacting to form A and B is very slow, right. So thus you only see accumulation of C and D. So that is what you see. So in that case for an irreversible reaction, what would you expect? That the equilibrium constant values in general will be relatively low, right. So let us look at what we have here. So I believe we have this particular case here, right. So let us look at this graph here, right, and equilibrium constants, let us say K equilibrium, right, and what do we have here? Let us go from bottom down. So first up I guess this violet colored here, which we are calling as irreversible, right, and what do we see here I guess, and pardon me I guess just minor mistake. So obviously here if the numerator is high, K is not going to be low, K is going to be high, right. A minor error in what I spoke earlier. So we were clear about that when the rate of forward reaction is greater than rate of the backward reaction, the numerator is going to be relatively higher, right, and you would see that thus if the numerator is obviously higher, that would mean that the equilibrium constant is going to be high. So coming back to our example, so that is what you would see here at a high. So whenever we call irreversible, what is happening here I guess? So everything is being transformed here, right, Ca is being transformed entirely here, right, and that is what you see here at a slightly low K equilibrium value, still more or less the same. When K equilibrium is 10, what is K equilibrium equal to 10, let us say, right, it still means there are 10 by 1. So again products by reactants, so still there are products by reactants ratio is more or less 10:1, right, that is what it means here, and that is the yellow line here I guess. And the next case is K equilibrium equal to 1, so 1 by 1, and that is why you see it is more or less near 0.5 I guess, right, the Ca by Ca naught is near 0.5, right, and as we keep going down what is happening I guess, the equilibrium is shifting, and when it is 0.1, what does K equilibrium equal to 0.1 means? Equal to 1 by 10, so there are more reactants rather than the products left, so the backward reaction is actually faster than the forward reaction. So rate of the backward reaction is faster than the rate of the forward reaction, that is what you see here. And as we keep going up I guess or keep going down, K equilibrium is 0.001, and what is that equivalent to? 1 by 1000, that is the product by reactant, layman's nomenclature here I guess. So what does this mean? Rate of the backward reaction is much faster than let us say rate of the forward reaction. Yes, again this is just for understanding purposes I guess, we are trying to relate equilibrium with kinetics, not a good way to do, but for your understanding we can look at those aspects I guess, right. So this is what we see here. So this is the irreversible reaction in the forward reaction when rate of forward is far greater than rate of the backward reaction. But as we keep moving up, what do you see though? You see that ultimately it ends up that rate of the backward reaction is far greater than the rate of the forward reaction. So here you have A being completely transformed. So initially all the A is converted to products, right. So in this case here you see that in the irreversible case A is completely transformed to the products, there is no more A after certain time. But let us say in K equilibrium equal to 1, right, if I guess this is the case for A going to B, let us say. All the sets of examples are for A going to B. What do you see, I guess, as A goes to B, again B is also transformed to A and so on. And again the other case, A going to B is much slower than B going to A. So what does this mean? Any A that transforms to B is immediately again transformed to A again. So that is what you see here. That is why you more or less see that the concentration of A is constant throughout. So that is at the other end of the spectrum. So anyway, we will move on to our next set of slides. So here we have factors affecting rate of reaction. So kinetics is always interrelated to rate of your reaction, right. So we will look at what it is or what are the factors that are affecting the rate of the reaction. So we already came across one term, rate constant. So obviously it is a constant for a particular temperature anyway. So rate constant, that gives us an idea about your particular kinetics. So rate is certainly going to be dependent upon your rate constant. It is a constant for a particular reaction though, A plus B going to C plus D. For this forward reaction you will have a particular rate constant, let us say, right. So the major aspect upon which the rate of the reaction depends is concentration of reactants, and this is remarkably important though. Why is that? So it only depends on, for this reaction as in A plus B or A and B going to C and D, what is the rate of this reaction depend upon? It is equal to R equal to K into activity of A or concentration of A into activity of B. And in this particular reaction we have no, what we say, variables that look at the concentration of the products. So it as in the rate always only depends upon the concentration of the reactants, right. So please keep that in mind, that the rate always depends upon only the concentrations of the reactants. So here it is the concentrations, right. So obviously though, if we are looking at the reverse reaction C plus D, so I will call this R1, C and D reacting together to form A and B. So for that R2, and this will be K1 and this will be K2, will be obviously equal to K2 into concentration of C or activity of C into activity of D, right. I think that is clear here. So in this reaction A and B are the reactants and C and D are the products. That is why you see only the variables that talk about or give us an idea about the reactants in this equation. And the second equation where C and D react to go to A and B, right, you have only the activities or concentrations of your, pardon me, C and D, right. So that is what you have here. Anyway, you can have concentrations here, that is not an issue, right. This should be concentrations, this should be concentrations, it depends on the concentration of your particular reactants, concentrations, right. So let us look at the different kinds of reactions that we have. So one would be 0th order, usually rarely do we come across this 0th order, right, and rate equal to a constant, and only in very rare specific cases do we usually come across this. The rate of the reaction is a constant, right, and B, it is a first order, and examples are A decaying to products, right, and what would be the rate of this particular reaction then? Rate is equal to the K or the rate constant for this particular reaction into the concentration of A. So this you see is 0th order, right, not 0th order, pardon me, the first order. And obviously again we will have in the same case second order, and we have multiple cases, I guess, A plus B going to products or 2A going to products. So rate would in this case be K times concentration of A into concentration of B, and in the second instance it is going to be the relevant rate constant into concentration of A into concentration of A. What does that translate into, I guess? That is equal to K into A square. So both of them are the second order. So the rate is first order with respect to A here, first order with respect to B here, and overall rate is equal to second order. right, and here the rate is second order with respect to A and also obviously second order overall. So, right, and the same case I believe you will have what we say third order, right, or 3A goes to products. So, rate will be equal to what now, K into concentration of A square into B, and this will be R equal to K A cube, or A plus B plus C goes to what now, products, and R in this case equal to K into A into B into C. So, in this last instance if we are talking about this particular the latter example, right. So, the order of the reaction is first order with respect to A, first order with respect to B, first order with respect to C, but third order overall, right, that is obvious here, right. In this case or the second case it is third order with respect to A and also third order overall. So, that should be relatively straightforward, I guess. So, then we have talked about how the rate depends upon the concentration now, right, and the other aspect we need to look at is temperature. I believe I have that in the next slide, right. So, temperature in general, this is the rate constant now, rate constant at a particular temperature, activation constant is exponential of energy of activation by RT, negative exponential, I guess. So, rather than boring you with the not the calculation, it is just arithmetic, I guess, right, basic arithmetic, basic calculations, K at time t by K T naught equal to exponential of energy of activation into T minus T naught by RT T naught. So, what does this mean? As you increase the temperature, right, in general the kinetics of your particular reaction are going to be higher, and that is something straightforward to. In general the rate constant, not in general, the rate constant is going to be higher, right. As you increase the temperature the faster the reaction it is. And the second case that needs to be looked at is that energy of activation has a huge effect on your change in temperature on Kt, and we will see why, I guess, not why, that is clear, I guess. So, even a small change in or change in energy of activation, let us say, will have a multiplying effect on your change in temperature here. So, the higher the energy of activation in general, greater is the effect of change in temperature on the relevant rate constant, right. That is what you see here in this particular equation, right. So, I think in different cases people also might have come across what is it now, different empirical equations, I guess, right, theta into T power minus 20 and so on, those are all empirical equations, that depends on the scenario that you are looking at, right. So, let us look at the other aspect here. So, stoichiometry, I guess. So, why are we concerned with stoichiometry here? So, let us consider an example here, example reaction, I guess, stoichiometric coefficient of A in compound A, B, that can go on to form, or let us say I am only going to look at one reaction here, going to form C. This is not R, this is the stoichiometric coefficient mu, I guess, right, D, right. So, here what is the rate of this reaction, let us see, what is the rate of this reaction now? Take a few moments to think about that, right. The rate of the reaction is going to be what now, the rate constant of this particular what do we say, equation, right, multiplied by the concentration of A raised to the power of that stoichiometric coefficient into the other reactant B raised to the relevant stoichiometric coefficient. This is the rate of the reaction though, right. But in general I do not just want to have information about the rate of the reaction though. I want to know how it relates to rate of change of A, rate of change of B, rate of change of C, and rate of change of D, right. I want to be able to come up with a metric that can equate all these aspects, and how do I do that, I guess, and obviously relate that to rate of the reaction here, and this is the rate of the reaction, right. So, for that particular case I am going to look at the stoichiometric coefficients, and I think we looked at this when we were trying to define the or calculate delta G, and so I am going to normalize that by the stoichiometric coefficients, right. And another aspect here is A and B are being lost and C and D are being formed. So, that is what you see here, right. So, this is a take home message that you need to keep in mind, right. So, what does this mean? So, this more or less means that rate of A is equal to minus, because it is being lost, stoichiometric coefficient of A into rate of your reaction, right. And for example, rate of D would be plus because it is being formed, stoichiometric coefficient is D into rate of the reaction. And what is the rate of the reaction? That is something that we have here, I guess, yes. And so, this is your basic stoichiometry though. So, I believe we are at the end of our class, but I need to still talk about one other aspect. So, the last aspect would be your, let us say you have complex set of reactions now. Right, how are you going to model them, right? And in general, as you move higher up the chain, right, you are going to use MATLAB to model various what do we say, phenomena that you observe, right. And in general, you can't, what do we say, look at individual reactions and such there. So, for example, we are going to look at A plus 2B going to C, okay, or 3C, let us say, and C plus 2A going to B, let us say, right. And so, have, let us say, numerous such cases, right. How am I going to go about it? So, I guess we will continue this in the next class, or look at how to model or set up the relevant reactions. We are going to look at RNet and such. So, we will briefly discuss what we looked at today and then wrap it up, I guess, right. So, we start talking about kinetics and how rate of the reaction is dependent upon the concentration, right, and it is typically Kc for A going to B, concentration of A, this is what we looked at, right. And we only always look at concentration of your reactants, right. We always just look at the concentration of reactants. The rate of the relevant reaction here, which is A goes to C, is only dependent upon concentration of A and obviously the rate constant here, right. And if it is A plus B going to whatever it is here, the relevant rate is R equal to K into concentration of A into concentration of B, right. That is what we have here, and it is a second order here, right. And we also looked at the effect of temperature. In general, the greater the or higher the temperature, the higher your rate constant or the higher your kinetics are going to be, right. And then we also looked at the effects of stoichiometry, right, and how to relate different rates of your particular compounds with respect to your rates of the reaction. And in general, we are going to look at a complex set of reactions in the next class, and I guess that is it from me for now, and thank you.